Carbon compounds. Although cells are 70 to 95% water, the rest consists mostly of carbon-based compounds. This includes proteins, DNA, carbohydrates, and lipids, which are mostly composed of carbon atoms bonded to each other and to atoms of other elements. These elements commonly include hydrogen, oxygen, nitrogen, sulfur, and phosphorus. Organic chemistry. Organic chemistry is the study of carbon compounds, and it also focuses on any compounds with carbon or organic compounds. Organic compounds can range from simple methane to complex molecules, like protein, that may weigh over 100,000 daltons. Nature of carbon atoms. Carbon atoms are the most versatile building blocks of molecules. With a total of 6 electrons, a carbon atom has 2 electrons in the first shell and 4 electrons in the second shell. Carbon atom has a little tendency to form ionic bond by gaining or losing 4 electrons. Instead, carbon usually completes its valence electrons by sharing electrons with other atoms in 4 covalent bonds. The property of elements to link with one another forming chains of identical atoms is called as catenation. Carbon exhibits catenation to maximum extent because of strong carbon-carbon bond and tetravalency. Due to this property of catenation, carbon atoms can form various straight chains, branch chains, or ring structures, thus giving rise to a large variety of carbon compounds. Since carbon-carbon is very strong, these bonds of carbon compounds are exceptionally stable. No other elements can exhibit its property of catenation to the extent seen in carbon compounds. Silicon may form compound with hydrogen, which have up to 7 or 8 atoms, but these compounds are very reactive since silicon-silicon bond is much weaker than carbon-carbon bond. Variations in carbon skeleton contributes to the diversity of organic molecules. Carbon chains form skeletons of most organic compounds. This carbon skeleton may include single, double, or triple bonds. This skeleton may vary in length and may be straight, branched, or arranged in a closed rings. Why carbon is special? There are 5 reasons why there are so many carbon compounds. First, carbon has the ability to form long carbon-carbon chains. Second, carbon atoms can bind each other not only in straight chains but in complex branching. Third, carbon atoms can share not only a single electron with other atom to form a single bond, but can also share 2 or 3 electrons forming a double or triple bond. Fourth, same collection of atoms and bonds but in different geometrical arrangement within a molecule makes a molecule with a different shape and hence different properties. And fifth, all of the electrons that are not being used to bond with carbon atoms together into chains or rings can be used to form bonds with atoms of several other elements. Hydrocarbons. These are organic molecules that consist only carbon and hydrogen atoms. Fats are biological molecules that have a long hydrocarbon tails attached to a non-hydrocarbon component. Functional groups. This contributes to the molecular diversity of life. Components of organic molecules that are mostly involved in chemical reactions. The number and arrangement of functional groups help give each molecule its unique properties. Saturated hydrocarbons, also known as alkanes. Alkanes are composed entirely of single bonds and are saturated with hydrogen. Alkanes is the simplest of the hydrocarbon species. It is also the basis of petroleum fuel and are found as either linear or branch species. They have their carbon atoms bonded in a straight chain. The general formula for alkanes or saturated hydrocarbons is CnH2n plus 2, where C stands for carbon atom, H for hydrogen atom, and N for the number of atoms. For example, propane. Propane is a gas at standard temperature and pressure, but compressible to a transportable liquid. It is a saturated hydrocarbons with 3 carbon atoms. Okay, so let's see the structural and molecular formula of propane. So we are going to use the general formula CnH2n plus 2. Since propane has 3 carbon atoms, we are going to substitute the N with the number 3. Okay, so that would result from C3, H2 times 3 is 6 plus 2, 8. So C3H8. Okay, so this is what propane looks like in its structural formula. We have 3C bonded singly to each other and with the remaining H or hydrogen atoms. IUPAC rules for alkane nomenclature. Alkanes with unbranched carbon chains are simply named by the number of carbons in the chain. The first 4 members of the series in terms of number of carbons are named as follows: methane, 1 hydrogen saturated carbon; ethane, 2 hydrogen saturated carbons; propane, 3 hydrogen saturated carbons; butane, 4 hydrogen saturated carbons. Alkanes with 5 or more carbon atoms are named by adding suffix A and E to the appropriate numerical multiplier. Hence, C5H12 is called pentane since it has 5 carbon atoms. C6H14 is called hexane, hex for 6. C7H16 is called heptane, and so forth. Alkyl groups. Alkyl is formed by removing 1 hydrogen from alkane chain and is described by the formula CnH2n plus 1. The removal of this hydrogen results in a stem change from A and E to YL. Okay, so take a look at the following example. We have here CH4, which is called methane. When it turns into an alkyl group, CH3, the name changes into methyl. Unsaturated hydrocarbons. Alkenes. Alkenes are hydrocarbons with a carbon-carbon double bond. Alkenes are also known as olefins. Alkenes are more reactive than alkanes due to the presence of double bond. IUPAC rules for alkane nomenclature. First rule, the ENE suffix indicates that it is an alkene or cycloalkene. Okay, Rule 1. The ene suffix indicates that it is an alkene or cycloalkene. Alkanes are named using the same general naming rules for alkanes, except that the suffix is now ene. For example, C2H6, so that is an ethane. When it becomes an alkene, turns into C2H4, and its name changes from ethane to ethene. Okay, rule number 2. The longest chain chosen for the root name must include both carbon atoms of the double bond. The parent structure is the longest chain containing both carbon atoms of the double bond. The alkene contains only one double bond, and that double bond is terminal or found at the end of each chain. It is not necessary to place any number in front of the name. For example, butane or C4H10. Its molecular formula is C3H2CH2CH3. When it becomes an alkene, name changes into butane, C4H8. Its molecular formula is CH2 double bonded with CH, CH2CH3. Rule number 3. The root chain must be numbered from the end nearest a double bond carbon atom. If the double bond is in the center of the chain, the nearest substituent rule is used to determine the end where numbering starts. The root chain must be numbered from the end nearest a double bond carbon atom. The double bond is in the center of the chain. The nearest substituent rule is used to determine the end where numbering starts. Okay, so for example, name the following compounds. So this is the compound. First, determine what is the name based on the number of carbon atoms. We have 1, 2, 3, 4, 5. Since it is 5 carbon atoms with a double bond, it is called pentene or 1-pentene. Why pentene? Because the double bond is found on the first carbon atoms. Can be also called as pent1-ene. Next, name these compounds. First rule, determine the longest chain by counting the number of carbon atoms with a double bond. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Since the longest chain is moving this way, it is the parent chain, and it is called as hexene. Since we have a substituent group which is an alkyl group as ethyl, we're going to name this as 2-ethyl-1-hexene or 2-ethyl-hex-1-ene. Why hexene? It has 6 carbon with a double bond. Why 1-hexene? Double bond is found on the first carbon. Why ethyl? The substituent group is an ethyl group, CH3CH2, from the saturated carbon, ethane. And why there is a 2 in this part? Because the ethyl group is attached to the second carbon. Rule number 4. The smaller of the two numbers designating the carbon atoms of the double bond is used as the double bond locator. If the double bond is not terminal, then the carbon should be numbered in a way as to give the first of the two double-bonded carbons the lowest possible number, and that number should precede the ene suffix with a dash. Okay, for example, we have here a 2-pentene or pen-2-ene. This is the molecular formula. CH3CH double bonded to CH, CH2CH3. Why it can't be named as pen-3-ene or 3-pentene? Because double bonded carbons should be assigned with the lowest possible number by counting this way, 1, 2. And it is not possible for this part to count from the left, 1, 2, 3, because it will give the double bonded carbons a higher number. Rule number 5. If more than one double bond is present at the compound, it is named as diene, triene, or equivalent prefix, indicating the number of double bonds, and each double bond is assigned a locator number. For example, we have here octa-2,4-diene. Why octa? Because there are 8 carbon atoms in this molecular formula. And diene because there are 2 double bonds located at the second and at the fourth carbons. While in this molecular formula, it is named as deca-1,5-diene since it has 10 carbon atoms and 2 double bonds found at the first carbon and at the fifth carbon. Properties of alkenes. Alkenes are carbon-carbon double bond, which changes the physical properties of alkenes. At room temperature, alkenes exist in all 3 phases: solid, liquid, and gas. Melting and boiling points of alkenes are similar to that of alkanes. However, isomers of cis alkenes have a lower melting points than that of trans isomers. Alkenes display a weak dipole-dipole interactions due to the electron attracting sp2 carbon. For example, of unsaturated hydrocarbons, propene. Propene has a 3 carbon atom. General formula for alkenes is CnH2n. So, substitute the number of n by 3. So, that would be C3H6. Okay, so this is the structural formula of propane. 3 carbon atoms with 1 double bond, and the remaining unattached atoms of carbon is bonded with hydrogen atoms. Unsaturated hydrocarbons, alkynes. Alkynes are hydrocarbons with a carbon-to-carbon triple bonds. Its general formula is CnH2n-2. Like alkanes, which have the suffix ene, alkynes uses the ending yne. If a molecule contains both a double and a triple bond, the carbon chain is numbered so that the first multiple bonds gets the lower number. So, let's take a look for the nomenclature of alkyne. First is find the longest carbon chain that includes both the carbons of the triple bond. Okay, so the longest chain would be this one. Consists 1, 2, 3, 4, 5, 6, 7, 8, 9. Since it has 9 carbon and a triple bond, it is called as non-9. Next, number 2. Number the longest chain starting at the end closest to the triple bond. A 1-alkyne is referred to as a terminal alkynes, and alkynes at any other position are called internal alkynes. For example, okay, so that is 2-9 since the triple bond is found on the second carbon. After numbering the longest chain with the lowest number assigned to the alkyne, label each of the substituent to its corresponding carbon. After numbering the longest chain with the lowest number assigned to the alkyne, label each of the substituent at its corresponding carbon. While writing out the name of the molecule, arrange the substituent in the alphabetical order. If there are more than one of the same substituent, use the prefixes di, tri, or tetra for 2, 3, or 4 substituents respectively. These prefixes are not taken into account in the alphabetical order. For example, that is 2-9, considering the longest chain. For chloro, for chlorine, and it is attached on the 4th carbon. Second substituent group is iodine or iodo. 6, diiodo. Since there are 2 iodine attached on the 6th carbon, going to use the prefix di for 2. And the last substituent group is methyl attached to the second on the 7th carbon. So the name of this compound is 4-chloros, 6-diiodo, 7-methyl, 2-9. Okay, part 2 of the rule number 3. If there is an alcohol present in the molecule, number the longest chain starting at the end closest to it and follow the same rules. However, the suffix would be -ynol because the alcohol group takes priority over the triple bond. So we have here this molecular formula, and that would be octane since it has 8 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8. 3 null because of the alcohol groups attached on the 3rd carbon. And 6 is for the triple bond, which is attached on the 6th carbon. 1, 2, 3, 4, 5, 6. And 7-methyl for the substituent group, which is an alkyl group attached on the 5th carbon. 1, 2, 3, 4, 5. So that is methyl. The name of this molecular formula is 5-methyl 6-octane 3-nol. Part 3 of rule number 3. When there are 2 triple bonds in the molecule, find the longest chain including the both triple bonds. Number the longest chain starting at the end closest to the triple bonds that appear first. The suffix would be used to name this molecule would be dine. For example, is this molecular formula. Okay, so find the longest chain with the both triple bond. So it is the longest chain. Then number the longest chain starting at the end closest to the triple bond first. So this part would appear as to be the first. So 1, 2, 3, 4, 5, 6, 7, 8. So that is octane. 1, 5. First triple bond is attached on the first carbon, and the second triple bond is attached on the fifth carbon. Then add the suffix -dine. And last, the alkyl group, which is methyl, attached on the fourth carbon. So this molecular formula is named as 4-methyl-1,5-octadiene. Rule number 4, substituents containing a triple bond are called alkenyl. So what is this rule number 4? For example, is this one. We have here a cycloalkane, which is cyclohexane. Its name is bromocyclohexane. Cyclo means it in a ring form. Hexane has 6. Bromo, for bromo, attached on the fourth carbon, a element bromine. And 1-chloro. The first carbon has an substituent group chloro. And the same thing is on the first carbon, there is an alkenyl, which is ethinyl. So the name of this molecular formula is 1-chloro-1-ethinyl 4-bromocyclohexane. Last rule for the nomenclature of alkyne nomenclature is a molecule that contains both double and triple bonds is called an alkyne. The chain must be numbered starting with the end closest to the functional groups that appears first. For example, we have here that is the longest chain, nonene, since it has 9 carbon atoms, and this chain consists both of the triple bond and the double bond. Next, 1,4, since the double bond and the triple bond is attached on the first and the fourth carbon. First carbon has a triple bond and the fourth carbon has the double bond. Then next, according to the rules, alkyl groups must be numbered according to alphabetical or arranged alphabetically. Ethyl attached on the 6th carbon. And last, methyl group, which is attached on the 3rd carbon. Therefore, the name of this molecular formula is 6-ethyl-3-methyl-1,4-nonene. Properties of alkynes. Alkynes are nonpolar unsaturated hydrocarbons with physical properties similar to alkanes and alkenes. Alkynes have slightly higher boiling points and dissolves in organic solvents, have slight solubility in polar solvents, and not insoluble in water. For example, ethane has a boiling point of negative 88.6 degrees Celsius, while ethane is negative 103.7 degrees Celsius, and ethane has a higher boiling point of negative 84.0 degrees Celsius. Okay, let's have an example. Propane, which has 3 carbons. Following the general formula for propane, which is CnH2n-2, substitute the N with the number of carbon. Since propane has a carbon number of 3, we're going to substitute it. Propane is C3H4. Okay, so this is the molecular formula and the structural formula of propane. 3 carbon with a triple bond and the remaining unpaired electrons of carbon is attached to a hydrogen. Functional groups. Alcohol. Alcohol is an organic compound with a hydroxyl functional group on an aliphatic carbon atom. Represent alcohols by the general formula ROH, where R is an alkyl group. Nomenclature for alcohol. The longest continuous chain of carbon atoms containing the OH group is taken as the parent compound, an alkane with the same number of carbon atoms. The chain is numbered from the end nearest the hydroxyl group. Okay, this is for rule number 1 and 2. Since it has 4 carbon atoms, it is butane or two all because the hydroxyl group is attached on the second carbon, and 2-methyl because the alkyl group methyl is attached on the second carbon. Therefore, its name is 2-methyl-2-butanol. Okay, rule number 3. If more than one hydroxyl group appears in the same molecules, or called as polyhydroxy alcohols, suffixes such as diol or triol are used. In this case, the E ending of the parent alkane is retained. Okay, so let's use this example. It is propane because it has 3 carbon atoms with a single bond. We have 3 hydroxyl groups attached on each carbon. Therefore, its name is propane 1,2,3 triol. Triol since it has 3 hydroxyl groups.